They are offering these not only the output reader that is outside for people to play with, but also they gently offer the help, the aid for some of you to come here. So at some moment they will be shown these and that guys are the special guys that are here just because Tarlac is very friendly and brought them here. But of course I'm joking because I like to joke a lot. But it's serious that it's important to have companies like those that understand that we are partners and that we do it for our lives. So at this moment we'll have Sergio Muniz, that is a professor here at VIII, as written there, the Instituto de Física de São Carlos, one of the institutions of Universidade of São Paulo. And Sergio is famous for some interesting things, not only for making interesting experimental physics. Nowadays he's quite devoted to NV centers, but in the past with atomic physics and etc. But he's also very famous for giving very long talks. So please do not allow him to talk for more than half an hour. And now they are having some issues, but almost solved. But the central idea is that if you have no clue what an optical tweezer is, you are in the right place for learning. If you have good ideas, you can also learn much more stuff. Or Sergio has already played with them for many interesting applications. And if you just want to test his knowledge, also be our guests. It's not helpful. Okay, forget about the switch and just use your finger and the keyboard. You also work. Classical technologies need more error correction than quantum.
Of course, we tested before, but when it's real, it's for real.
You know that old history of the guy that got a box of matches and passed all of them. Okay? So I already introduced you, probably you didn't follow, but please Sergio, thank you very much for coming, not only for driving me here, but also for participating, for giving this lecture on optical tweezers. And please people, enjoy Sergio's lecture.
Thank you Marcel. It is my pleasure. You just make sure that the other one will work too. Which, of course, is not. See, if you forgive me just for a second, let's make sure that we're starting here. Did it change something? Here, now at least the keyboard is working. We fix one cable, the next one comes. It will work. So it looks like this is probably some sort of Alright. Okay, now try the other one. Maybe it works now.
So you are having a practical lesson on how a physics lab works.
Yes. Indeed.
Every time something does not go smoothly, and then you start searching for with the reason for things not to work smoothly.
Yeah, so this is part of our routine in the labs. So I have prepared here, I have keyboards, I have all sort of stuff. Hopefully one will work.
Someone told you that redundance was good?
Alright, now so thank you for the opportunity, and thank you very much for the nice words, kind words, Marcelo. So it's really a pleasure for me to be here. Since everyone, I'm not the first, as I understand now, but I'm one of perhaps the second speaker that's coming to this conference for the first time. I'm enjoying it very much so far. Looks like we fixed it. Wonderful. See? In the end, somehow it works. Thank you very much. Okay, so it's really a pleasure to be here. I'll be talking about some of the things we do in our lab, but I try to, in the spirit of this school, to make it more of overall pedagogical experience for people that perhaps haven't been exposed to some of these ideas yet. So, by the way, just raise your hand if you know or work with optical tweezers before, so just I know. Oh, that's great. Not many. All right. Thank you. No, so it's probably about the right.
Sergio, can we make the complementary question of who has no clue what an optical tweezer is?
Yes, that's a better question. All right. Oh, perfect. Good. So be well. Perhaps I did the right thing then. First, let me give credits where credits are due. Probably the main reason why I'm presenting this here is because the students in our institute, the student chapter in São Carlos, here, invite me to present an introductory lecture, just basically the main ideas, to a very broad audience of students, possibly students from high school and all. So for that presentation, I start from very, very basics, like high school kind of optics, to build up the intuition to understand what's going on. And because I was not sure, I put also some information for people that, as a matter of fact, was mostly students from grad students or undergrad students that actually attended the meeting. So you will see there's a lot of stuff. I don't want you to worry about some of that. I'll try to guide you through the process, what's most important. And my expectations are actually very low, and I will be very clear about what I expect you to get or to be able to understand and maybe tell to other people later after the presentation. But again, if you are interested in learning more, and if you speak Portuguese, because this was even in Portuguese, you can see the presentation in the YouTube, or you don't have time for like this, of course. You can use the QR code if you want. And I'm also calling your attention to, this was a mini course that also was organized together with our labs. And the students from the student chapter prepared a presentation explaining how the educational kit works. The video, their presentation is here. I invite you to look, because in the presentation they will explain the educational kit from our labs. Of course, you should go outside also and see and try for yourself. I hope if I'm somehow successful, maybe you will be curious enough after this presentation to do so. But in Rafael's presentation, he actually goes through explaining every part of the details, and you connect how the main diagrams and the ideas that I'll be mostly talking about here is actually connected to a physical thing, and you can talk to Giovanna outside, and she probably can explain you too. But I know there's another reason why I'm calling the attention here, because Rafael was kind enough to borrow me some of his slides, and I will make use of them, and just to be fair and give them credit, you will recognize them because I will normally use it for showing them like that. Okay? All right. So, let me just take a look at the clock. So, those of you that heard about optical tweezers most likely heard or know about the Nobel Prize in 2018. Maybe some of you know or heard about that and still don't know about optical tweezers. And this is mainly why is the purpose of this presentation. So recently, it was awarded Nobel Prize in Physics for the development of one of the parts of the Nobel Prize of 2018. And that part was for Arthur Ashby. And the theme of that award was the developments using light and lasers in general. So the other awardees, Gerhard Moreau and Donna Strickland, worked with ultra-fast optical pulse lasers. But the history behind optical tweezers is actually rather long. For you, is probably an ancient history. It started in the 70s. It's actually kind of old even for me. So the first work on optical tweezers, one of the first works by Ashby is here. And the reason I'm calling this is not just because of historical reason, but because this work in the early 70s actually spawned a lot of the developments that we have in our community in quantum technology and quantum devices, mainly using atoms. So these ideas here stimulate a lot of development in optical trapping of lights, ions, and as you see, also larger particles. So these are works, and you see this is one of the first papers that he shows that you can produce force with a laser light. And here is another famous paper, now with Stephen Chu, another Nobel Prize winner, now in mid-80s. That was the first proposal for optical trapping and magnetic optical traps that will lead eventually to BECs, ion traps for a quantum computer, whatever. You probably noticed yesterday Fernando Brandão mentioning about the heat barrier platform, heat barrier atoms platform using optical tweezers. So this is just to give you a general view, but this history is kind of old. I mean, there's a lot of development in the field, and actually when I started working with optical trapping in the 90s, optical tweezers as such was kind of old. You know, you would see this and see, okay, this was like the first generation of ideas. Now we can do this with better ways, with atoms, and with more powerful, and so on. And so for like 10 or 20 years, I didn't pay too much attention to what was going on with the optical tweezers, the way I would describe to you today. And you may be wondering why I'm telling you that. Is because, well, part is because the early developments of optical tweezers, since they were introduced, were actually very powerful in biology. So a lot of these studies were done in biology, manipulating cells or structures, and I will give you a hint, just a hint of that in some of the slides coming next. But just to give you a better picture, and why I'm telling the story, why it is relevant to worry or want to learn about optical tweezers today, maybe it's better communicated in this review article in Nanotechnology about a decade ago, 10 years ago, where they called the attention for, let's call, newer or more recent developments in optical tweezers, filling this region here in the middle. And I'll explain how it comes about later. So here, in this is a scale shapes showing some of the systems that can be optically trapped and have been optically trapped and manipulated. So here you see a size, a scale for the sizes. So you go from angstroms to micrometers, tens of micrometers. So you can track atoms, molecules, NV centers. As a matter of fact, all the ones that are highlighted here are the ones that we have done sometimes already for one reason or another. And maybe I will mention one of or few of them later. But it's not the main goal of this presentation. It's just this slide is mostly to show you how versatile is the tool to track small particles. And then you start to understand why this is an important technology for this community, for instance. Because if you want to control and manipulate small things, nanoscale things, down to atoms or ions, or even perhaps smaller depending on the technique you use, but I would say atoms, you can use light. And not just that, you can use the interaction with the light to manipulate and control your system. So this is sort of unprecedented, and a lot of the technologies that we have today that give rise an opportunity for what we call the quantum 2.0, or the context that we mostly are interested in quantum technologies, comes from the fact that you can prepare, initialize, and do interesting things with these small quantum systems, from small to larger scale. So in that context, light is perfect to do that, and optical tweezers is definitely one of these tools, right? So I mentioned here that these highlighted systems here are some of the systems we track in our labs. I would not have time to get into the details, but I will just mention here molecules, because there's a poster from Larissa is here. She will be presenting a poster Thursday, telling you a little bit about the things that we've been thinking about to do with molecules as a platform to actually study quantum thermodynamics. I'll leave to her to explain it later, but I could not avoid to put you on the spot. And the other one, of course, is the one that I'll be talking about for those of you who will be here next week on the workshop with NV centers. Although in that presentation I will not be talking about trapping NV centers in optical tweezers, but this is something we did in our lab too, and that is trapping nanodiamonds with NV centers. If you don't know what NV centers are, that's another story, not for today. But I wanted to mention that just some examples of these kind of technologies that can be pursued, and so on. And of course, atoms. My lab has been working with tracking atoms, producing different atoms, VCs and stuff for more than 10 years. So this is one of these technologies in the other side of the scale. So, okay, so as Marcelo told you, I not quite fairly have this reputation of talking too much and talking for not really, respecting the time. So I will do my best effort. So if I have to cut short this presentation, I want you to get a few things and a few ideas. This is one of them. So the first one is this slide. This is why I put it right in the beginning. Because the first message that I want you to take home is how versatile is light, not just optical tweezers per se, but light in general, but let's call, in this sense, optical tweezers, the ability to trap and manipulate and control objects in a broad range of sizes. And that when you go about describing it, say calculate forces or whatever you are interested, there are mainly three limits that you should be aware of. And my goal for today is basically to explain or give you a hint. Explain this one because I think it's rather easy. This is the one that you can use basically high school physics to explain the main ideas. And the other ones here, this one, the intermediate one is actually the most complicated one, is the nano tweezers regime, it's the intermediate sizes. So when things are kind of large or too small compared to the wavelength of light, it's kind of easy to describe the physics of optical tweezers or optical trapping in general. So for particles that are much, much larger than the wavelengths, you can basically use geometric optics, and it's fine, and I'll show you how, if you haven't heard about that before. If things are actually too small, like an atom or ions or nanoparticles, say smaller than 100 nanometers, that's actually kind of easy too. And I'll briefly explain how you do that. The intermediate region is actually the more complicated one, where you have to use heavy math. basically electromagnetic theory, scattering theory to do that. It's not that complicated, not for you, but it's certainly more involved. And I'll give you just a hint of the main ideas and some references for you later. So the main idea that I want you to take home from today is optical tools are cool. Optical tweezers are cool, are nice systems. They are very versatile, and they work. You can think of them in three limits. For things that are too small, then we use what is called the Brady limit, or the dipole approximation limit. I'll explain later. And if things are, say, in the range of micrometers, you can just basically use geometric optics. You can explain it to high school students. Intermediate region is a little more complicated, to say the least. And I'll just give you a brief information from that. This picture is just meant just to show you sort of on the scale how it goes, the intensity of the interaction, the force, compared to the sizes. And you see that there's a region, as you go smaller, the force increases up to a point and then it drops very rapidly. So if you say here micrometers size, the force is not too strong, and it gets stronger as you go here, but if you try to trap atoms or molecules or nanoparticles, then it's a matter of ratio for surface to volume and so on. But the important thing is that it drops very fast, and if you want to produce this calculation here, the dashed lines are actually the limits for the geometric optics and the Rayleigh limit. And the solid line is the full electromagnetic theory that describes it completely. Right? Okay. So these are the main ideas. Three limits, very general. But for those of you that may be interested in learning more, certainly will not learn everything here. There's no time for that. Neither do I know all of that. But if you don't speak Portuguese and don't want to see the YouTube video that I mentioned in the beginning, here are a few review articles that I find very, very didactic, very pedagogical that you may be interested. And this one here is very nice. It describes basically most of the things, almost everything I'll talk about here from the thesis itself. And there's a version of that available in the archives here. And check on that later. By the way, nowadays, there are textbooks, and this is one of the best that I know, and I used several of the images and illustrations from this book in this presentation. So if you really want to know about the state of art on that, this is definitely worth a check. If you're lucky enough to speak Portuguese and you want to brush off in your knowledge on optics to understand some of the ideas that I described, there's this nice book from Professor Sergio from São Carlos as well. Those of you who don't speak Portuguese, I'm sure you will not have trouble finding good optics books as well. All right? So let's go. Let me just give a brief general idea of how these things work. I want to at least get the gist of how it works and get the impression how an experiment, science experiment of that is performed. And of course, if you want to see details of at least an education version, you can see outside. This is a view, one of the views of the setup, one of the basic views of our setup. I don't want to get into too much detail. I just want to give a general view of the lab, so you have a sense for the scale. You can have it outside as well. But I will mostly focus on diagrams like this, and I apologize. There are some figures you noticed are still in Portuguese. I couldn't translate that in time, so but I'll try to guide you, and if you have questions, please ask. All right. So the main idea here is the following: you basically have a microscope, or something that works like a microscope. In our lab, actually, we built our microscope. Mostly, we're using the optics here, this high quality numeric aperture objectives that are commercial. And the other parts we actually do ourselves, the mechanics, because we want to have. It's not just about money. It's actually about versatility for the experiments. We want to insert beams in different directions and do things and control and stuff. And you cannot do that in a typical commercial microscope. But basically, the main idea here is the microscope. you have a laser, of course. In our setup, we have some way of modulating the position of the laser. We use an acousto-optical modulator to do that. The other parts are not essential for the main ideas, except perhaps this one. There is a detector that gives you the position of the whatever you've been tracking here. I will not get into the details how that works, but I can just give you a brief idea here. This, you could actually just take a picture and analyze the image, and I'll show you an example later. But here we're using, in this setup, in this configuration, we're using what's called a quadrant photodetector, basically 4 photodetectors, and by measuring, just to give you an intuition, how the light is distributed in these photodetectors, you get the position X, Y, and Z. It's not clear, not so obvious how it works, just from that description, of course, but it's not complicated. If you were interested, I can explain to you later. You also find that in the references that I mentioned before. But I told you that I had a goal for this presentation. The goal is that at the end, you have an idea, basic idea how it works, and can understand something that's shown here. This is basically an histogram of the position of the particle, the trapped particle. All the information you get from the system is in here. So that's why we call it the attention. You have to use some sort of device to get the position of whatever you're tracking. An atom, a molecule, a microsphere, nanoparticle, nanotube, whatever. AV centers, whatever, all right? So we use such devices and will depend on the applications, but in the end we build things like this. There are these histograms. So I'm showing this slide because there is another one at the end. So Marcelo, I expect to get to that slide, even if I have to speed up a little bit later. But I want you by that time that you understand how the main idea works and you are able to understand the information and why it's relevant that is shown here. All right? Okay, so just a basic view, overall view from the setup. I already mentioned several of the things that we tracked. This is a top view. I show here an acousto-optical modulator that allows us to do things like trap particles and see how they move when we do that. Some examples of traps, things that we tracked, nanotubes, and the centers. This is the fluorescence from the nylon, which is much, much smaller than the optical resolution limits. So, but we can see them because they fluoresce. That's the same idea that we use for the molecules, by the way. And getting this information, in this case here, we have an example for a microsphere, a trapped microsphere. This is an old video, so I apologize for the quality, but you will see here one trapped particle, and it's jumping. Well, it's jumping not, in this case, not because of mechanical vibration, but thermally. There's some vibration as well, but these main jumps, the bigger jumps that you were seeing, are actually produced by the optical potential, the light and trapping potential that we're switching. And we do that for several reasons and experiments, and I'll explain how we analyze that later. Just to give an idea of sort of the resolution, here's data from our experiment. In this case here showing that we were able to position and separate very easily up to or down to 20 tenths of nanometers, and this is by no means the limit. This is just the limit that we had for that setup in that particular configuration. So it can, in this case, we were tracking a particle that was like 2 micrometers in size, and we could position and control it to, let's say, 10 nanometers resolution. Using more sophisticated technique, you can do better. You can certainly have more resolution for the measurement that we use in this technique in particular. And the reason that I'm showing you here is it's not just to give you how small it is, but it's mostly because the way we do and produce these potentials, modulating these potentials, we can actually produce things that are not just like springs, not like harmonic potential kind of things. And this is an example of a double well potential. Using more sophisticated techniques to modulate light, you can basically design the sort of external potential that you can apply to the particle or the system that you're interested in studying. There's a reference here from these measurements if you're interested. And just to make it more fun, taking advantage of Danielle that's here, it's another worldwide experts in structural light. Here I'm showing you an example of, I'll show you just for fun, an experiment of a particle that we trapped and using light, not just single beam light, with some structure, in this case a Laguerre-Gauss beam, that can be encoded using a spatial light modulator. We tracked some particles, in this case here, some very interesting particles that we were interested in. Wow. Okay, so I will have to really jump to the but anyway, we were studying that and using orbital angular momentum, Laguerre-Gauss beams, we could trap them, and apply a twist torque, if you wish. Here it's running, it's spinning. Oops, sorry. Should get used to the button here. Here it's spinning to the left, and the other one to the right, just because of the orbital momentum of light. This is the particle. It's an interesting one because it has some particular shapes, and it's a microscopic in the microscale object that's built out of very small foils that have some particular geometry. This is isomers, geometric isomers that we were interested in studying at the time. There's a reference here if you want to learn more. And here is actually one of the things that I think absolutely amazing. These studies started in in 80s or late mid 90s that studying molecular machines or nano machines, living molecules, like in this case here, or proteins in this case, like kinesin or APP synthase, that are very important for biology. I don't have time to explain that. And this, of course, is a model because these objects are much, much smaller. They're like nanometers. They're really nanometers mechanical machines that have been tracked and used optical tweezers to learn information about, very relevant information about the system. I will just mention one here. This is a paper, a science paper, early 2000s from Carlos Bustamante group, where they tracked that and tracked a molecule like DNA and do experiments in these molecules to study stochastic thermodynamics at the time. But today, in the current day, we're interested in studying things like this for quantum systems, like Jarzynski equation, Paraty relations and fluctuations relations, things like that of course I will not have time to explain. But okay, let me at least transmit to you the very basic idea. I'll jump through the other details from the electromagnetic theory, because I promised you that I want to at least get a very basic idea how this works. So this is the simplest one. That's basically just using optical geometric objects. So here you have a laser. You have the refraction of a laser in a sphere, just a glass sphere, for instance, and it's of course suffer refractions here in the surfaces, and then it's changing direction. So it's changing the momentum k from the light. So there's a change in the linear momentum of light, which is shown here. So this for the simple idea. So if the light changed the direction, something made it change the direction, which was the particle, right? So the particle had the reaction force from this action on the light, and this is basically the very elemental principle how you can actually do force in a dielectric particle just by changing the linear momentum of light. Of course, this will not trap the particle, just the way I do that. You have to do a little more than that. You have to use the microscope. But if you analyze the ray beam, the light beams, if you wish, and consider that now you have a Gaussian distribution, which means that the intensity of the beam is higher in the center than the edge, you actually create a situation that you can trap the particle will tend to be trapped here, given that the index of refraction of this particle is larger than its beam, say water, glass and water, for instance. And you can work it out yourself. It's actually very simple to convince of that. There's a reference here for more information. So in the end is, if you do that, if given right conditions, you will trap a particle in the center of an intense beam, a Gaussian distributed beam. But you also do a force, a scattering force that pushes the particle towards in the other direction. This light is called scattering light. So there's two components here. And for the optical tweezer work, you have to balance them out, or in the general case, you want to have a stronger gradient force. So the other one that brings it to the center is called gradient force. So if you want that to be larger than the scattering force, it's not difficult to do that. That's mainly the reason why you have to use a microscope or a very good lens. The geometric optics is very simple conceptually, but it's not necessarily the simplest one to calculate, actually. I'm just showing this slide here just to show you that if you follow these light rays, they bounce more than once in the surface, so you have to account for that. The calculation is actually more complicated than the case, the dipole force approximation. I will jump through that. And just to remind you, this is basically the description from the geometric optics. If you go to the other limit, the Rayleigh limit, the dipole limit, which is for atoms or very small particles, the theory is somewhat involved. You will probably not be able to explain that to a high school student, but certainly you can explain that to undergrad students, like physics 3-level kind of discussion, not much more complicated than that. The main idea that I want to give you here is that if you're using something like an atom, a molecule, or something that is small enough, basically you can divide the optical force into two categories. The scattering force, this one here, basically the linear transfer of momentum from light to the atom, for instance, or the dipole force, the conservative force. This one you can actually talk about the potential, an optical potential for it, because it doesn't dissipate. This one actually produces cooling. This is what is used for laser cooling, trapping atoms, lowering temperature, and so on. I don't have time to explain that, but it has to do with the scattering of these photons and the process involved. But the other important message that I want to give you here is that for this dipole force, it depends basically on the gradients of the intensity of the light. So given the light intensity profile, you calculate the gradient, and it will point in the direction of the highest intensity. That's the direction that the force will point. And it's basically a bunch of constants depending on the system, but it will depend directly on that map, on the intensity gradient. And it also depends on the tuning of the light with respect to a relevant optical resonance of the system. If it's an atom, if you're below the resonance or above the resonance, the force actually can push or pull the atoms depending on the tuning. So this is another information. That's what we use to manipulate atoms, do BECs and interesting experiments. The force, it's summarized here. I didn't mean for you to understand, it's just to give you the reference. But it basically, I just meant to say that it's depending on the intensity of the gradient in the square of the electric field. But it's actually more complicated. But if you just have a Gaussian beam, the important part is that basically to a very fair, good approximation near the center, you have sort of a Gaussian profile, a little more complicated, but sort of a Gaussian like this, and near here, in the end, in the center, you basically have a harmonic potential as everything in nature, right? So everything is harmonic potential, given that you're close enough to the tracking position. But believe me, it's a lot simpler to calculate this than actually to use the geometric optics for the positions, conditions that it applies. Of course, the intermediate region is a lot more involved. It involves to use heavier math to describe the electromagnetic field, basically scattering theory. I will not bother you with that. It will give you some very nasty looking terms, which are not all that complicated as they look. So when you first encounter them, this here has more terms that I have time to explain. But again, the reference have all the details for you. The main part that I already explained is the shape of this curve. And here the solid line gives you what the scattering theory, full theory gives you, and the dashed lines, the dotted lines, the dashed line here is giving the approximations and for the Rayleigh limit or the geometric optic limit. I'm almost done. Marcelo is laughing. He knows me. quite well known, right, myself. But anyway, so I want to keep my promise. You understand that diagram. For that, there's another bit of information that you need, and this is the fact that if you're trapping a particle like in a fluid, it also has thermal energy because it's in fluid. It has Brownian motion, collisions, and so on. That's actually how we learn about Brownian motion in the first place, as you certainly know. And it means that if you have a particle there in a fluid, it goes doing a Brownian motion like this. You can describe that too. It goes by the name of one of the ways you describe that for a classical system is to use something called the Langevin equation, which has an odd, scary name, but it's actually very, very simple. I'm sure any of you here will understand. And that's the kind of thing that you can also explain to an undergrad student. Is basically is the harmonic oscillator, damped harmonic oscillator that you learned like in introductory physics second semester, plus a stochastic term. That's basically a random force. This is a very phenomenological way of describing it, of course, but it's good enough. I'm going to show you that data that I showed you is basically using that. I will not get into the details. I just mentioned that you can actually write a very simple equation of motions for the system that we have in the lab for microparticle strapping, because we basically have an equation like this, which is even simpler than the damped harmonic oscillator. You see here, this is not acceleration, this is velocity. This is because you're already in the over-damped limit. So the equations of motions are very simple, except for the fact that you have this stochastic term. So this is technically a stochastic differential equation, which is not so nice to do, but it's not too complicated either. All right. So this is just to give you a basic idea of the physics, how it goes about if you have, let's say, classical particle trapped in the physics, and that will help you to understand that slide that I showed before. So here is like the position of a particle that is not trapped, the diffusion of a Brownian motion particle, and here is sort of what you would see for the distribution, not the data, it's just what of the density distribution, probability distribution of the particles if you apply the external potential to it. And if you trap it, you see something like this. If you trap the positions, you will see something like, you can draw something like this, and depending the way you want to show it. All right. I will not get into the details, but I want to give you an idea how you actually do the things in the lab. So you trap them, you have these particles in a harmonic potential, plus these stochastic terms that is causing Brownian motion. How do you go about to get the data? Well, you use one of the detectors, or even take an image like this one here, and then you do some image processing and get like the centroid of the particle, whatever you want to do, depending on the necessity, the precision you need, of course. But say you have a distribution of positions. From that distribution of positions, you do a grid, you beam the positions, and you write, and you get from that data a histogram of positions. So we're almost there. We have the histogram of positions already, right? So you have that, and you have a particle that say is in thermal equilibrium with the fluid. So it follows a Boltzmann distribution for the position, which depends on some external potential, trapping potential, and here is the stochastic force, the temperature, all right? So basically doing a fit, basically I'm just assuming that I have a harmonic potential. This is an assumption that is fair enough for many cases. And if it's not the case, and you know how is the external potential that you're designing, say you're using SLMs or more fancy things to design your double well potential, whatever, you have the expression for the potential, so you can actually do a fit to the data, the histogram data that you get, and get the parameter. In this case, you're using harmonic potential, you get the constant, the force constant for the trap potential. This is actually, if you've been paying attention, this last slide is actually from Rafael. This is actually data that he got from using in the demonstration that he used in that course. And if you watch the video later, you see the details. Here is the one that I showed you before. So in here, in the last, not the last slide, at least the last slide that I meant to communicate to you today. And I hope now that you understand what you're seeing here, why you're seeing this histogram, and how you get from this histogram to relevant parameters for trapping and how the optical tweezers work. and so on. You can do a lot of interesting things with these systems, but unfortunately today Marcelo will not allow me. I'm joking, Marcelo. I'm very pleased to be here. Thank you very much, and thank you for the picture. So this is the people from the lab. I have been fortunate to have many bright and talented, hard-working people in the lab. Here, they're just some of the more recent. Some of these people already moved on, graduated and moved on. I just want to call attention for Talita. You probably have seen her several times. That's because she built the apparatus that you saw, that I showed you. Now Larissa is taking the Larissas. There's Larissa Nolasco here. There's another Larissa working on other experiment. Working that. Talita is almost done with her PhD. So I thank you very much for your attention and patience.
Quick question. No raised hands. I hope you got the idea of what the wizard is. If not, you have one there to play and time to ask Sergio. He will stay here up to the last talk. And a bad news, he's the one in charge of the last talk of the workshop. But the Festival da Cachaça starts just after this.
By the way, now you probably know.
It's big. It's okay. Just talk.
Thank you. Now you probably know why he put me in the last talk of every session I talk. So I have the pressure of finishing because there's the poster section, and in the last day, I'm the last speaker of the last day, the last session. So everybody is leaving the room, and then I feel the pressure of leaving. So these are what friends do. Marcelo, thank you very much.
There's something about drawing emotion and how to have extra time when you need a talk. So just be friends with the chair and.
Anyway, if anyone has questions, I'll be around.
Exactly, he'll be around. And now we'll start our organization for the poster session. So please, it's very important that you remember the suggestion that if you will show your poster and you want to see the output wizard, run, go now. Okay, exactly. You are one of the privileged guys that other ones will attend the idea that you should see there before. If you are not showing your poster now, we would like to have the help of something like 5 to 10 of you to put things in order here. Not more than 10, not less than 10. Self-organize yourselves in order to help us and pay attention. Exactly. So if you are not one of the